Alright, welcome back. We're in section 5.4, which is simplifying radicals. So we're going to start with a kind of overall concept here. If I have a radical with whatever index of one number, and if I multiply that by the radical with that same index, whatever index is here has to be here for this to work. But the radical, the nth root of a multiplied by the nth root of b, can be considered to be the nth root of a times b. So this is our kind of fundamental property for this section here. It works in order to simplify a lot of stuff, like say, let's look at the square root of 4 multiplied by the square root of 25, right? Now I could treat each of these separately. The square root of 4 happens to be 2, and then I multiply that by the square root of 25, which happens to be 5, and this is 10. Right? But I could also say that this is the same thing then as the square root of 4 times 25, which is 100, and the square root of 100 is 10. So I get the same number either way that I look at this, right? And that's kind of what we're looking for in this section, ways to simplify bigger expressions, and this is, well, step 1, right? If I have, let's say, a cube root, let's say I have the cube root of 5, which I can't do anything with, I can't simplify this, right? But let's say I want to multiply that with the cube root of 7. Again, I can't simplify this, right? Well, I can simplify the entire expression as simply the cube root of 5 times 7, so I would multiply that together, it's 35. I can't simplify this any further because the cube root of 35, there is no nice integer number that multiplies 3 factors up to give 35, so this is as simplified as that can get, and we're done with this one. But that may not always be the case. If I have, let's say, the cube root of 3, again, I can't simplify that, and I have the cube root of 9, which I also can't simplify, right? Because it's not the square root of 9, which would be 3, it's the cube root of 9, which is not an integer. But I can take this and call this the cube root of 3 times 9, which is 27. 27 does have a cube root. 27 is 3 times 3 times 3, so the cube root of 27 is 3. And I've simplified this expression all the way down just to a nice integer. Right? So sometimes it works out nice to do this. Sometimes we can simplify some of our factors out of a root. So for example, if I had, say, the cube root of 24 multiplied by, let's say, the cube root of 36, right? Well, I can call this the cube root of the product of 24 and 36, and it may not always be advantageous to actually multiply these together. Because to figure out what I can pull out of a cube root, I want to factor this down. So multiplying this is making a big number, which then I have a big number that I have to factor down. And I could easily just say this is my first movement of that factorization process. So I can just start here. I can say, well, 24 is divisible by 2. That leaves me with 12, which is divisible by 2, leaving me with 6, which is divisible by 2, leaving me with 3. So from the 24, I have factors of 2, 2, 2, and 3, which already I can see that I can pull out a group of 3 2s. This 36 I'm going to factor down. I'll say it's 6 times 6, which gives me 2 times 3, and then 2 times 3. Right? So again, I need 3 factors in order to pull this out. So here's a group of 3 2s. I can pull that out as a 2. But there's 1, 2, 3 3s as well, so that's going to come out as a 3. And the only thing I have left over is this 2 and that 2. So I do have stuff left over, but on the outside I have a 2 times 3, so that's a 6. And inside that cube root, I still have this 2 and that 2, multiply them back together to give you 4, right? So I can pull some stuff out, I can't pull everything out, but I've simplified it as much as I can. All right, good. Okay, let's look at some expressions with x's in it. So let's take maybe the 4th root of 4x to the 3rd and multiply that by 4th root of 8x to the 3rd. Well, individually I can't simplify either of these. 4 doesn't have a 4th root. I mean, it doesn't have a nice 4th root. And x to the 3rd, there's not enough to pull out, right? 8 is just 2 times 2 times 2. That's 3 factors of 2, so I can't do anything under a 4th root. Likewise with x to the 3rd here. If I multiply these two together, that gives me the 4th root of 4x to the 3rd and 8x to the 3rd. And everything in here is just multiplication, right? It's 4 times x to the 3rd times 8 times x to the 3rd. But again, to pull out of a 4th root, I'm just going to break everything down. 4 is 2 times 2. 8 is another 2 times 2 times 2, right? 2 times 2 came from the 4, 2 times 2 times 2 came from the 8, and then I have x times x times x times x times x times x. Or I could call it x to the 6th, right? But we can think of it this way. There's a group of 4 2's here that I can pull out. There is a 2 left over, and so I have to leave that under my 4th root. And there's a group of 4 x's here with 2 left over, and so I can pull out that group of 4 as just an x, and then my 2 that are left over stay down there, and I've simplified it. I can pull 2x all the way out, but I'm left with a 2x squared inside the 4th root. And that's as simple as I can get this one. All right. Let's look at a big root. Let's look at the 6th root. Let's say 8x to the 5th. And multiplied by the 6th root of 16x squared. So again, individually I cannot simplify either one of these roots, but if I put them as a single root, the 6th root of 8, and I can rearrange these all I want because it's going to be 8 times x to the 5th times 16 times x squared, so I'm just going to put the numbers first because I can. And I'm going to have x to the 5th and then 2 more, so I might as well just write it as x to the 7th right from the get-go. I can write 8 as 2 times 2 times 2. 16 as 2 times 2 times 2 times 2, right? I need 6 to pull out of here, so I've got 1, 2, 3, 4, 5, 6. And once again, I have to leave 1 behind. So 2 comes out. Under the 6th root, a 2 is left. And then I can pull 6 of these 7 out as an x, and I'm left with the 1 left over. So I have 2x times the 6th root of 2x. Good. Now, similar to, we've seen this before, but we've seen the square root of a divided by the square root of b is the same thing as the square root of a over b. This works even if you have an index that is not necessarily 2, right? But we can go both ways with this. Sometimes it's advantageous to go one way, and sometimes it's advantageous to go the other. So let's look at one of these. If I'm asked to simplify let's say, I'm going to steal this from the book, I have the root of 12x over the square root of 3. we might have seen this before, but if I have something like this, I can then just say, well, this is the same thing as the square root of 12x over 3. I can actually simplify 12 divided by 3, which is 4. So that's 4x under the square root, and I can take that x out, right? I'm sorry, not the x. I can take the 4 out. The x has to stay. So this then would be 2 times the square root of x, and I'm done. That's as much as I can simplify. Likewise, it might be advantageous to go the other way. Let's say I have the cube root of, say, w to the 6th over 32x to the 6th. This fraction doesn't really interact with each other, so I can write this as the cube root of w to the 6th over the cube root of 32x to the 6th. So then I can treat each of these differently, or separately. W to the 6th under a cube root, that's just simply 2 groups of 3, so that is w squared. 32 happens to be 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. So 32 is just 2 times 2 times 2 times 2 times 2. I need 3 to pull out, so I can pull out a group of 3 of them, so I can pull out a 2. But I have to leave, I pulled out 3, I have to leave these guys, so that's a 4 under my cube root. But x to the 6th is again 2 groups of 3, so that's x squared. And I'm done, right? Be careful here, that looks like a 23. My spacing, let me just push this guy a little over. 2x squared times the cube root of 4, and that's as good as I can get this one. Okay. All right. Let's take a look at just one more of these. Let's say I have the cube root of w squared x to the 5th y to the 7th over the cube root of w to the 7th x to the 5th y to the 2. Right? Now because each of these has w's and x's and y's, it might be advantageous to call this simply the cube root of the fraction w squared x to the 5th y to the 7th over w to the 7th x to the 5th y squared, and then simplify inside the fraction before I worry about the cube root. So then I'm left with the cube root of, well, the w's simplify to be a w to the 5th in the denominator. The x's completely cancel out, and then the y's simplify to be a y to the 5th in the numerator, right? So I have this, the cube root of y to the 5th over w to the 5th. Now that these two, the numerator and denominator, aren't going to really play with each other, I can call them separately. So the cube root of y to the 5th, the cube root of w to the 5th. Y to the 5th is one group of 3, so that's a y that pulls out. But I have 2 left over, so y squared stays. And likewise with the w to the 5th is one group of 3, so I have a w that pulls out and 2 that stay. Okay. And I can write this as it's written here, or I could write the cube roots as one cube root. It doesn't really matter. Either one of those would be fine. Okay, thank you, and I will see you guys next time.